All right, so let's go back and we'll take the reaction that we looked at earlier. And how do we determine which direction an acid-base reaction will proceed? So the first thing that we need to do to be able to figure it out was we need to have a reaction written out. So here I have a reaction written out where acetic acid reacts with ethoxide to form acetate and ethanol. And then the next thing that we need to know is we need to know what the pKa's are. So the pKa here is 4.76. That's the pKa for acetic acid. And the pKa for the ethanol is 15.74. So now we have to think about what those two numbers mean. pK of 4.76. Okay, is that more acidic or less acidic than 15.74? It's more acidic. If this one's more acidic, this one's less acidic. And what does more acidic mean? More acidic means that it gives up its proton more readily. Which means that this one holds on to its proton more. So you can think about this sort of like a bit of a tug of war. Who wants the proton more? So the stronger acid, the more acidic molecule, wants to give up its proton more. The less acidic molecule wants to hold on to its proton more. So the direction is always going to go from the more acidic molecule to the less acidic. Because this one wants to give up its proton and this one doesn't. So what that means is that if I mix acetic acid with ethoxide, the reaction will go this direction to form acetate and ethanol. However, if I put in ethanol and acetate together, if I mix these two, really nothing is going to happen. Because those two don't want to react. Then you can actually even quantify how much this reaction is going to proceed in this direction by the difference in the pKa's. So in this case, the difference in pKa's is 11, pKa difference of 11, which means that this reaction will proceed to the right 10 to the 11 times more than to the left. And with huge numbers like that, we would really say that this reaction goes completely to the right. Or to products as shown. Now that we're starting to be more familiar with acids and pKa's, let's look at the factors that determine acid strength. Anything that stabilizes A- or the conjugate base is going to make HA a stronger acid. So this is a very useful principle. So anything that makes A- more stable and happier with its negative charge is going to make HA a stronger acid. And we'll see there will be 4 factors that will affect this. First, and this is going to be the most important factor, is an element effect. And the element effect really is which atom has the negative charge. And it's a fairly simple rule. More electronegative atoms are more stable with a negative charge. Okay, so that's the first rule. And we'll see how that works in a series of compounds as we go across a period. We'll have another rule that we'll learn in a minute that happens as we go down a group. So as we go across a period, so let's talk about a CH versus an NH versus an OH versus FH. So the way to look at these is we can look at the pKa's. So the pKa of a typical CH is around 50. The pKa of a typical NH is around 38. pKa of an OH is about 16. And the pKa of FH is 3.2. So, how big of an effect is this element effect? As we move one element over from carbon to nitrogen, which will be more electronegative, this becomes 10 to the 12 times more acidic. And here, when we move from NH to OH, it's 10 to the 22 times. And then once again, when we go from OH to FH, it's about 10 to the 13 times. It's an enormous difference in acidity as we move across the periodic table from carbon to fluorine. Okay, so now what happens when we move down a group? So now we're going to look at the difference between HF to HCl to HBr to HI. And now if we look at the pKa's, HF is 3.2, HCl is -7, HBr is -9, and HI is -10. So now we see something different happening. So here are the conjugate bases: fluoride, chloride, bromide, and iodide. So fluoride is the most electronegative atom. However, the difference that we're seeing here is each time as we add a shell, we're making these atoms much, much, much larger. So another key factor is that charges are stabilized when spread over a greater area. Okay, so the charges will be stabilized when they're spread over a greater area. That's why I-, which is much, much, much bigger than fluoride, I- is much more stable on its own than F- is. All right, the second most important effect is a resonance effect. And the resonance effect says that whenever two or more Lewis structures can be drawn for the same arrangement of atoms, then the molecule is going to be more stable. The molecular ion will be more stable. Okay, so if we're going to look at an example of this, the example that we were using before, and that is ethanol versus acetic acid. Okay, and we'll look at pKa's again. pKa of ethanol is about 16. The pKa of acetic acid is about 4.8. So now here, if we're going to try to look at stability, we're looking at the alkoxide versus the carboxylate. And now from element effect, oxygen has a negative charge, oxygen has a negative charge. So there's no difference as far as the element effect. Now there's still a difference here of 10 to the 11. This is 10 to the 11 times more acidic on this side. Well, why? Well, obviously because we're in the resonance effect. So here, there are no resonance structures that we can draw of this alkoxide. The negative charge is isolated on that oxygen. However, I can draw a resonance structure here that delocalizes that charge between the two oxygens. And of course, we can draw the resonance hybrid, partial negative charge on each oxygen. And that's really the structure that we have. It's in between each of these. And that delocalization of that charge, rather than having the charge isolated like we do on alkoxide, how important is that delocalization? It makes that 10 to the 11 times more acidic. That's how big of a deal that delocalization is. So you can say if your conjugate base is going to have the charge delocalized, that's going to make its conjugate acid stronger. So this acid is stronger because it's got a more stable conjugate base.